Okay, so now I want to investigate the stability of Euler methods. So whether these methods are going to blow up in time as we use them, or there should be a criteria in which kind of tells us and informs us about the stability of these methods and their evolution in time. Okay, so let's get started. Okay, I'm gonna start here. Stability of Euler methods. So we'll start with an example and then move forward so you understand what is going on, and then move forward to general method of finding stability for these Euler methods. Okay, so example. I'm gonna look at du over dt equals to minus kappa u for t greater than 0 and u at 0 is u0. Okay, let me show it this way. Is u0. So I want to plot it as well. So this is t time, and this is u0, so u0 at time 0, and this is u. Okay, so the analytical solution, if you solve it, it's going to be something like this. Okay, and now we want to solve this numerically with these Euler methods. Okay, so first I want to solve it with forward Euler method. So forward Euler. Let's see what would be the stability of this method. So for a forward Euler, we have to evaluate du over dt plus kappa u at tn, right, equals to 0. So our approximation will be un plus 1 minus u at time n over delta t equals to what? Equals to minus kappa u at n, right? And so u at n plus 1 is gonna be 1 minus kappa delta t at un. So this is how I can evolve in time. Okay, So let's now see what happens if we choose different kappa delta t's, if we choose different delta t, and whether it really matters the delta t that we are choosing, okay? So here I'm gonna have n, the time, and then the second one I'm gonna have kappa delta t equals to 1/2. The next one I'm gonna have kappa delta t equals to 3/2. And the last one, I'm going to have kappa delta t equals to 5. Okay, and here I have n. So n is going to be 1, 2, 3, and 4. Okay, so for 1, if I calculate it, kappa delta t equals to 1/2, and u1, I'm gonna set that to u0, I'm gonna set it to 1. So let u0 to be 1. If u0 is 1, then at n1 for kappa delta t, you're gonna have 0.5 here. If kappa delta t is 3/2, we are going to have minus 0.5 here. And if it is 5, you're going to have minus 4 here, right? The next step, these are going to be my u1, right? Then I'm going to have u2. For u2 is going to be 1 minus kappa delta t u1, right? So I'm gonna calculate that. So this is gonna give me 0.2. This is gonna give me 0.25. This is gonna give me 16. The other one, this is gonna give me 125. This is gonna give me minus 125. And this is gonna give me minus 6. This is 25. And so you can go on and on for all of this. And you see they are giving conversion to different numbers. So let's plot them here. So for example, for the first one, first we have 0.5, then we have 0.25, then we have 125. Okay, so if this is 1, then the next one, let me show it with blue, is going to be here. Then I have something here. Then I have something here. Okay, so this is the first one. How it evolves in time. Okay. And then the other one kind of oscillates. So the first one is minus 0.5, then I have 0.25, then have minus 125. So the first one is going to be around here. Then the next one is going to be here. Then the next one is going to be here. So it's kind of oscillates, right? So I have something like this. Then this, then this, and then this goes on and on, okay? And the last one, which is this, it also oscillates, but it also grows a lot. It grows very fast. So the first one is going to be minus 4, something like around here. Then the next one is going to be 16, something around here, for example. Then the next one is going to be minus 6, so something around here. So it's just a lot. It just oscillates a lot. So let me just plot it. So it's going to be something like this. Then it's going to go way up. Then it's going to go way down, and this just continues. So you see, not all of them converge to the analytical solution. So for example, the green one, which is this one, is going to be unstable. It just goes up and up, right? So it doesn't converge. So it really depends on the k delta t that we choose, whether we are going to converge to the analytical solution or no. Okay. And here, maybe the analytical solution yeah, the analytical solution here, I mean, it could have been a little bit closer to the actual solution. I could have plotted it a little bit closer to that, so you can understand it better. So as you see, the blue one and also the blue one kind of converges to the analytical solution as we go up. Okay, so it's kind of stable. So this is, let me see, this is the analytical solution, this is kappa delta t equals to 5. This line is kappa delta t equals to 1/2. Kappa delta t equals to 1/2. And this line is kappa delta t equals to 3/2. Okay, so you see, it really depends on, the solution really depends on the kappa delta t here. So the blue one kind of converges to the analytical solution. The purple one, which is kappa delta t equals to 3/2, it oscillates, but it finally is going to also converge to the analytical one. However, the green one is not going to converge. It's not going to get to what we want, and so it's kind of unstable. So these two are stable, and this one is unstable. Okay. So as you see, from the analytical solution, we expect that as n goes to infinity, un becomes 0, right? So from the analytical solution, as you expect, it should go to 0. And so u1, let's see what, so let's see why this is the reason, and whether we can kind of formulate it and find a criteria for stability for this forward Euler method. Okay, so u1 equals to 1 minus kappa delta t times u0. Okay, this is u1 based on here, forward Euler method. Okay, I just wrote the forward Euler method. So u2 is gonna be 1 minus kappa delta t u1, which is 1 minus kappa delta t square u0. Okay, and this goes on and on until un. So un is going to be 1 minus kappa delta t to power n u0. Okay, so if I name this 1 minus kappa delta t, let me write it here. If I name it as lambda, This is gonna be what? This is gonna be lambda n u 0. Okay. So in general, I can say a general statement that u n plus 1 over u n is gonna be lambda. Okay. And a general statement for stability says that if the absolute value of u at step n plus 1 over u at step n is smaller or equal to 1, then we are going to have stable. We are going to be stable, right? So it means that if your solution is going down, your un is going down, then you are going to have a stable condition here for this problem. Okay, of course, for different problems it's going to be different, but for this one. And if your solution is growing, like if your un is gonna un plus 1 is greater than un, it means we will not converge to a value, so it's gonna just blow up. The solutions are gonna blow up, right? So it's gonna be unstable. So this means that lambda, the absolute value of lambda, should be smaller or equal to 1. Okay, and what is lambda? The lambda is 1 minus kappa delta t. So this should be smaller or equal to 1, and we will have two conditions here. It means 1 minus kappa over kappa delta t should be greater or equal to minus 1 and should be smaller or equal to 1. Okay. So the first one means the first equality is minus 1 should be smaller or equal to 1 minus kappa delta t. So let's see what this gives us. This gives us that kappa delta t should be smaller or equal to 2. And the second one is 1 minus kappa delta t should be smaller than 1. So this means that kappa delta t should be greater than 0. And this means if kappa is positive, delta t should be greater than 0, which it is, right? So it's kind of a trivial thing. So the stability criteria here that we found is interesting, and it means that only and only if kappa delta t is smaller or equal to 2, then we will have a stable condition. Otherwise, we will have unstable condition. Okay, so let me write this down. This means kappa delta t smaller or equal to 2 will have a stable, otherwise unstable, and solutions and numerical solutions blow up. So this means we have conditional stability in this situation. Conditional stability for forward Euler method. Okay? So for forward Euler method, If kappa delta t is smaller than or equal to 2, we will have a stable, which is these two cases, right? We are stable. And if it is greater than 2, for example here, then we will have unstable condition. And the solutions are going to blow up, okay? So now let me investigate this method for the other two approximations that we learn. The first one is going to be, the other one is going to be backward Euler, and the last one will be variable weighted Euler approximation, okay? So let's start with backward Euler. So the backward Euler, the approximation was un plus 1 minus un over delta t equals to minus kappa un plus 1. I just want to note, like, these are not power, okay? Just don't confuse it. These are not powers. These are just time steps here based on the convention that we define. So don't confuse it later on. These are time steps. I think I said it here, right? So these are not like u to the power n. Okay, this is just a time step here that we do and we show. Okay, and as I said, if you are confused with that, you can just write it like this: un plus 1 minus un over delta t equals to minus kappa un plus 1. Okay, but in order to make it different than the spatial discretization, and this is a convention, we usually write it at top. Okay, so these are not power. Don't confuse it with power. So this gives us un equals to 1 plus kappa delta t times un plus 1. So the lambda here, which is going to be un plus 1 over un plus 1 over un is going to be 1 over 1 plus kappa delta t. Okay. And for delta t greater than 0, then 1 over 1 plus kappa delta t, which equals to lambda, is gonna be what? Is gonna be smaller or equal to 1. Right? So lambda, the absolute value, is always smaller or equal to 1, and this means we will be unconditionally stable. So backward Euler, what was the advantage of backward Euler? So the disadvantage is, as you see here, okay, for this problem it's not that difficult because we can simply put this here, but in other problems it can be more complicated because for example, if this is your f u, then you need to know the fun plus 1, but you don't know that, right? So this can be complicated in such problems, but for example, especially if you have a nonlinear function here, so you need to solve some matrix algebra. So that is a disadvantage of this method, but the advantage is it's unconditionally stable. No matter what you choose, what time step you choose, you are always going to be, your numerical scheme is going to be always stable. Okay. However, for forward Euler, you need to be careful about the time step that you choose. There is always a criteria in which your numerical scheme is going to be stable. And that is what we call conditional stability, okay? So this was for this, and then I think I don't have time for going through the variable weighting, the stability of variable weighting scheme. So I will do that in the next lecture. And now I just wanna, because that has many points, it depends really on this theta, whether you're gonna be forward, backward, or Crank-Nicolson. You can have different stabilities. And so let me just review what we learned today, okay? And then we will cover that in the next lecture. So in this lecture, we started talking about Euler methods, which were time marching methods, right? So we started with this approximation for initial value problems, general first order ODE, and how we should numerically solve for that. So we said we are going to discretize the domain, and then we approximate du and dt and fut using nodal values of u. So we introduce Euler method, and we will have other methods as well, like Rangakuta and Adams-Bashforth methods, but Euler one is the simplest one. And we started with the forward Euler approximation or explicit Euler method. And this is when you just start with, so you are seated here at t0, and then you will just evolve your u to one step ahead. You calculate your function at u0 at where you are seated, and then you can get your final solution, okay? So this is explicit, meaning that you can explicitly solve and update u1 at each time step, okay? This is order delta t. The advantage of this is very simple to implement with codes, but the disadvantage is that it might be unstable. The backward Euler approximation or implicit Euler method is where when you sit here, and so you have to evaluate your function for the future value of u1, which you don't know. So you might need to do matrix algebra in more complex cases. And this is also order delta t. The disadvantage, as I said, is it might be harder to implement, but the advantage is it's unconditionally stable. The variable weighted Euler approximation is a combination of these two methods, forward and backward Euler. So this is the approximation. So theta times the u1, which is the future value of the function, and 1 minus theta, the older value of the function. If theta is 0, we have a forward approximation. Theta is 1, we are going to have backward. And if theta is 1/2, we have a new approximation, which is called Crank-Nicolson approximation. And the advantage of that is it is order delta t squared. So we are actually increasing the accuracy of our finite difference approximation. Then we started talking about the stability of Euler methods. So we started with a simple example to illustrate what it is. And for example, for the or forward Euler method, which is going to give us this for this example, we showed that depending on the kappa delta t, the time step that you choose, your solutions, numerical solutions might behave differently. For example, if your kappa delta t is small, you're going to gradually converge to the analytical solution, while if your delta t is large, for example, this green one, you might kind of blow your solution, numerical solutions might blow up, right? So if you, for example, write this, you can simply, just as a practice problem. So as a practice problem, let me just say practice. Let me just write it down here. Practice problem. Implement this in MATLAB or Python and set and change kappa delta t and see your solutions for n equals to a big number, for example 100,000. Okay, and what you will see is for example, if your delta t is large, you will see that MATLAB is going to give you, for example, inf, which means infinity, or nan, right? So this is because your solutions are going to blow up. So here it means that your delta t needs to have a criteria and should be small in order for your solutions to be stable. And we found that criteria by defining this lambda, which is the value of u at the next step over the value of u at the current step. And in order to have a stable case, because your un as n goes to infinity goes to 0, your un plus 1 over un should be smaller than 1 or equal to 1. And so based on this, we found the criteria for stability, and we found if our kappa delta t is smaller or equal to 2, we will have a stable numerical scheme, forward Euler scheme. Otherwise, it will be unstable. Okay, so this method forward Euler is conditionally stable, or conditional. It has a conditional stability. Okay. On the other hand, backward Euler, if you calculate that, and if your delta t is greater than 0, this lambda is going to be always smaller or equal to 1, and thus your solution, your numerical scheme, is going to be unconditionally stable for this case. Okay? So this is the advantage of backward Euler method. So in the next lecture, I am going to look at the variable weighting method, and you will see that it is both stable, unconditionally stable, and in second order accurate for Crank-Nicolson method. Okay, so it has both advantages of these two methods. Thank you very much, everyone.